Okay, so thank you very much. Thanks for the invitation. I'm really happy to be here. So I'm going to talk about joint results with Jean Bourgain and Svetlana Zhitomirskaya. Actually, a significant part of these results were obtained when I was a member here 2 years ago. It was a great time. So this talk will be about interacting quasiperiodic particles. Each particle will be a particle on the Z lattice, so it's a one-dimensional discrete Schrödinger operator. And when we talk about two particles, its Hamiltonian becomes an operator on Z2. So let me write down the model. Okay, so it's a self-adjoint operator in L2 of Z2. So this term is the discrete Laplacian. So it's an operator which takes the sum of values of psi over all nearest neighbors. Psi is a function of two integer variables. So, and you can, if you forget about this term, you can look at it as direct sum of two one-dimensional Schrödinger operators, because two-dimensional Laplacian is direct sum of two one-dimensional Laplacians, and this is okay. So and this is a separable potential. So what about the potential? The potential is quasiperiodic. So its values of potential is a discrete sequence, and it's obtained by taking some trajectory of irrational rotation. So let me say that V is a one-periodic function. Let's say also real analytic. So T1 is one-dimensional torus, and amigas is some irrational number. Okay, so we're considering this model of two particles. So the potentials are the same, and you choose possibly different initial phase for the rotation for each of the particles. But you can also use the same θ1 and θ2. So in the study of quasiperiodic operators, it's natural to consider the whole family over the change in θ1 and θ2 rather than a single θ1 and θ2. And even if you want to prove the result for a single θ1 θ2, in the end you'll need to consider the whole family because of the proof techniques. Okay, so the first two terms is essentially direct sum of two one-dimensional Hamiltonians, which represents two particles which do not interact and do not have any statistics. And the third term is some interaction potential. So it's a function of two variables multiplied by psi. And we will be interested in the question of Anderson localization for this system. Anderson localization means the following, that if the coupling lambda at the potential, so this part we'll call disorder, because it's kind of not deterministic. It's not really random, but it's kind of oscillates because amiga is irrational. So general kind of idea is that at large disorder, systems like this should demonstrate Anderson localization, which means purely point spectrum with exponential decay eigenfunctions. And original motivation for Anderson localization comes from random models, where the sequence of values of the potential is just some random IID sequence. But after that, after results for random models are obtained, people also study different models which are deterministic but behave in some sense like random ones. An example of that would be quasiperiodic operator at large coupling with some Diophantine condition on the frequency, which I'll talk about a bit later. So let me now say why this particular model may be interesting, and also a little bit of context for this. So there are actually three reasons why I would think this is an interesting model. So first, motivation from random appearances. So it's the simplest possible case of many-body localization. Many-body localization is localization for a system of many particles. And it's a random analog of this model is studied very well in papers by Eisenman and Warzel, and it says that actually in this particular case, if lambda is, for any lambda, if the interaction is sufficiently small, then the system will be localized. So we cannot obtain this particular result, but we can obtain something like this. So the system is like a quasi-periodic analog of a well-known random model. So this is one motivation, just what kind of stuff we can do. Second motivation is that actually this particular model, well, actually a special case. So by the way, can you see this board? Can everyone see this board? Not covered by this? OK, good. I'll use all space. OK, second source of motivation is that a particular case of this model was actually first appearing in physics papers. So v of x equals cosine 2 pi x. It's called almost Mathieu potential. And the interaction potential is also quite special. Let's say u of n1 and 2 equals some function f of n1 minus n2, which is something natural to expect, right? So particles, the strength of interaction depends on the relative position of the particles. So yeah, coordinate n1 describes first particle and 2 second particle. So, and f is a function, let's say, with finite support, or even just a delta function at n1 and 2. So this particular model was studied in some physics papers. So some people I would name Fram and Shepelyansky. There's a paper in 2015, and there's a bunch of more papers. And their conclusion was not very rigorous, and they say the following thing, that suppose you consider a non-interacting system, and suppose you're in the regime where non-interacting system is localized. This regime is well known. And then we start adding interaction, like this. And they claim that after addition of interaction, quasi-periodic systems behave a bit differently from random systems. So random systems kind of preserve interaction, and quasi-periodic system show some kind of delocalization in some regime of not very strong but not very weak interaction. And we want to prove something rigorous related to this. We are not going to exactly recover the result, but we'll try to provide some rigorous insight. And the third motivation is like a more technical one. It's what's the place of this model in the general context of quasi-periodic operators. And from this point of view, you can look at it as a two-dimensional quasi-periodic operator. So, but a very special case. In general, two-dimensional quasi-periodic operators are generated by a function of two variables on a torus. So general two-dimensional quasi-periodic operators. So instead of this particular separable function, you consider a function of two variables with two different frequencies. So let's consider the potential of the form, let's say w n1 omega 1 plus theta 1 and 2 omega 2 plus theta 2. So, and this model is a particular case of this model if omega 1 equals, say, omega 2, obviously. And w is a sum of functions of one variable, right? And this model has been studied. There is a 2002 paper by Bourgain, Goldstein, and Schlag, and 2007 paper by Bourgain, who covered the case of any dimension. And yeah, so what's left to prove here? Well, the trick is that you can never prove localization for all frequencies. You have to remove some frequencies. So I already mentioned that you need some Diophantine condition, and in most cases, you have to remove some extra parameters, including extra frequencies. And it turns out that all the two-dimensional proofs that are known actually look not just as frequencies separately, but as a frequency vector. And to show localization, you have to remove a set of frequency vectors of positive measure. And then we are kind of in trouble, because the set of frequency vectors that we are considering has zero measure. It's, we are interested specifically in the diagonal vectors. And then it's not clear whether or not these methods can be modified to make sure that the vectors we are interested in are not, at least not completely removed. So this is an interesting question from the technical point of view. And it turns out that there are actually some extra effects related to the case of omega 1 equals omega 2, which you cannot see on this level. So I will explain that in a moment. OK, so this is some general context. Now I can start talking about the results. Yeah, by the way, so let me formulate, at least in words, general result that can be obtained for this potential. I will not write it down, but I'll say. So for every epsilon, there exists a sufficiently large lambda such that if you remove a set of frequency vectors of size epsilon, so it's possible to remove a set of frequency vectors of size epsilon such that on the remaining set of frequency vectors, the operator will have localization. So this is a typical two-dimensional result. So we can remove arbitrarily small but finite subset of frequency vectors, such that on the remaining set we have localization, but the smaller the set we remove, the larger coupling has to be. And we can prove something like this in this context, but I'll have to introduce several things to talk about particular classes of V and U that we're going to cover and explain what are the differences and special cases for the case of diagonal frequency. Okay, so I'll now talk about two things. So first, classes of V and classes of U. So let's first talk about, yeah.
Maybe I don't know. A lot of people don't know so much about localization or quasiperiodic. So maybe we could just review the single one-dimensional case. Is that?
Yeah, maybe just a couple of words. Yeah. So in one-dimensional case, so you look at the operator on Z of the form delta plus V and omega plus theta. So delta is one-dimensional Laplacian. This is just multiplication operator by the sequence. And yeah, you can put coupling constant lambda. And in one-dimensional case, the following is true. So there exists lambda 0 that depends V, such that for every lambda greater or equal to lambda 0, this operator family has Anderson localization for almost every omega and theta. So basically, you're allowed to remove a set of frequencies of 0 measure, and on the remaining part, you'll have localization. So,
and say again what you mean by localization.
Yeah, localization means that the spectrum is purely point, and all eigenfunctions decay exponentially. So basically, on the physical language, it means that the particle is trapped. It cannot propagate. It stays localized in the same area if you start the dynamics. So yes, in one-dimensional case, so the following is true. If the coupling is sufficiently large, then okay, so potential, let's say it's also analytic. If the coupling is large, then you have Anderson localization for almost every omega and theta. If coupling is very small, then actually there is purely IC spectrum.
What do you call coupling?
Coupling lambda. So, okay, so H has Anderson localization for almost every omega and theta. And if lambda is much less than some lambda 1 of V, then sigma of H is purely absolutely continuous. And this is some constant contrast with random model. So in random model, in one dimension, so it will have localization for all couplings. In higher dimensions only for large couplings, but on one dimension for all couplings. And here there is a transition. So for small potentials, so the spectrum kind of looks like the spectrum of the Laplacian, which is continuous. And for large lambda, it looks like the spectrum of the diagonal operator, which is purely point. And there is some transition in between. And the nature of this difference actually comes from something that's called duality, which I will not explain in detail, but let me just say a couple of words. That the cases of large lambda and small lambda can actually kind of be transformed into each other by some analog of Fourier transform. So if V is a cosine, then this transformation just changes the roles of the potential and V. And if V is a general analytic function, then after duality, the dual potential will become cosine, and the Laplacian becomes a long-range operator. But basically, usually to prove AC spectrum at small coupling, it's sufficient under some conditions to prove localization for large coupling of the dual model, which is possible. So, yeah?
Sorry, may I ask a stupid question, but really, when you say spectrum, you have the parameter lambda here.
Yes.
When you speak about spectrum, it will be eigenvalues which are not this lambda, but some.
No, lambda is not a spectral parameter. Lambda is fixed. So we look at this operator as an operator on L2 of Z. And look at the spectrum of this operator. So we're looking basically for eigenfunctions, essentially. E is a spectral parameter. Yeah, OK, thanks for the question. So, yeah.
So the analog of this, of the existence of purely absolutely continuous spectrum is also expected for 2D, right?
So at large coupling, yes, it actually can be proved, but I don't think it's written yet. So, okay, so the main difference between random and quasiperiodic operators is that for quasiperiodic operators there is some duality between large coupling and small coupling. And for random there is no such thing. So Laplacian and potential are very different objects. Okay, yeah?
Is there any restriction on what V you can have? Like V can't be the zero function, right?
Well, so V is an analytic one-periodic non-constant function.
Okay, so that's all.
Yeah, real analytic.
You think of cosine, right? It's good.
For example, cosine. Yes. So the most interesting case is actually the cosine, although there are some things which are more simple for this function. So yeah, if V, for example, is smooth even C infinity, then it becomes much harder question, like orders of magnitude harder, and there are no good results about general C infinity potentials, unless there is some transversality condition that's okay. So any more questions about maybe this introduction? Yeah, so as I said, for quasiperiodic case, large coupling is kind of similar to small coupling, not precisely, but in some sense. And this is why, okay, so it's usually harder to prove localization than for random case, but it's easier to prove delocalization for small coupling by duality. Sorry?
What is the dual problem?
So for this particular one, the dual problem would be the following. So okay, so h psi of n equals v hat convolution psi n plus 2 cosine n omega, okay, and here, and omega plus theta. So then lambda is going to be here. So I don't want to talk about precise definition of the duality. Basically, you have to consider not just single operator, but the whole family, as theta runs over the torus, and consider the direct integral of these operators. And then on the level of these direct integrals, you have to do a Fourier transform both in the discrete variable and in the theta variable. And one of them needs to be a little bit twisted by adding n omega. So then this theta will become this n, and this n will become this theta. So the dual model will be a long-range operator with relatively simple potential. So
if V is cosine, then it's even better.
yeah, if V is cosine, then the dual is basically the Laplacian. But large coupling changes to small coupling, because coupling is now at the Laplacian.
Actually, this transformation in quantum mechanics, you're exchanging x with exchanging position element. It makes sense that this.
Well, it's yes, actually. Okay, so I can tell you just two more words about this. So this model originally quasiperiodic operators. One of the sources of this is a operator on Z2 with constant magnetic field. So constant magnetic field, you can choose it to be periodic either in horizontal or vertical direction. You can do gauge transform to switch from one to another. And then basically in the periodic direction, you do the Fouquet expansion, and then theta will be quasi-momentum. And on the level of 2D operators, this gauge transform that chooses which direction will be periodic is actually duality. But on this level, it can be used as a Fourier transform on the level of direct integrals. Okay. Okay, so let me get back to this problem. So if you want some more general stuff, let me know. I'll stop. But now I'll talk about this particular case a little bit. So let me talk about the class of potentials that we're going to discuss here. So as I said, V is a real analytic one-periodic function, non-constant. So V and let's also assume without loss of generality that V has zero average. And then the new thing which you can see on this level is the following, that the result will depend on whether V has some kind of symmetries. So we say that V is symmetric so essentially if V of theta equals negative, okay, why do I say theta here? Okay, let's say theta. So it's either odd or v of theta plus 1/2 is negative v of theta. Okay, so maybe after some translation. So if v satisfies one of these two properties, or both, after translation of the argument, then it's called symmetric. Otherwise, it's called asymmetric. So, and you can see that cosine is actually symmetric. So, and it turns out that the results we're going to prove will depend on whether v is symmetric or not. So if v is asymmetric, we'll be able to prove the results over the whole spectrum. If v is symmetric, we'll have to remove some energies from consideration.
Isn't cosine negative theta equals to cosine?
Yeah, sorry. Yeah. So cosine is symmetric after translation. So actually, it's sine which is symmetric. Yeah. So I mean, I didn't write it, but I said that v is called symmetric if this property is satisfied after translation of the argument. Yeah. Yeah, so I didn't write the general version.
So your torus is normalized to be 0, 1.
For example, yeah.
Okay.
But cosine satisfies the second.
Yeah, cosine satisfies the second one because second one translation invariant, but you can also make it satisfy this one after translating. Yeah, thanks. Okay, so and yeah, so the reason the place where these conditions appear is basically when you solve the following equation: v of theta 1 plus v of theta 2 equals E. So for the proof, it will be important that the solution set of this equation does not contain any straight lines. And it's relatively easy to show that under these conditions that the only possible energy for which it can happen is E equals 0. So basically, we look at the equation v of theta 1 plus v of theta 2 equals 0. Then in the case of cosine, you'll have something like this. So we have 4 lines under 45-degree angle. And these lines will actually make really problematic to prove the localization. So these lines will be the reason why the proof doesn't work. OK. So this was about the class of potentials V. Now let's talk about the interaction potentials.
So
yeah?
away from E, then you're going to have, you want some curvature in this.
Yes.
You want some curvature in your level lines.
Yes, exactly.
What is the meaningful assumption that the average should be 0?
Well, it's just to say that, I mean, if we shift V, then it's just shift of the energy in the spectrum. So it's just, it will be convenient for the formulation to say that the removed energy will be 0 plus something else. I mean, if this is not assumed, then the statement will be just have one extra line. OK, so now let me talk about the classes of U. So U is a general interaction potential. So in particular, this is the most interesting case. But it turns out that the proof works for a bit more general class. So we say that, OK, so class of U. So first, we want U to be not very strong. So norm of U in infinity less equal than, let's say, constant C1 of U. Let's say constant C1 CU1 times lambda. So the results will be at large lambda. And so originally, when we proved this theorem first time, we basically said that let's fix U and take large lambda. But it turns out that we don't have to fix U in the beginning. We just need to fix this constant. So then the proof will work as long as U is not very strong compared to lambda, which is much better because it basically means that the interaction doesn't have to be weaker than the disorder. It can be stronger, but not like order 1, it's stronger. If the second condition is strong.
Something small then, or what?
No, C can be large. It can be like 1,000, million, just something bounded. So what's important is the second condition that I'm going to write down. So first this, not very large. And second one, which is called low complexity condition. So 2. So this condition, I mean, it might take took some time for me to realize, but basically it's the following thing. So suppose you take a box of size m, and you take all translation of this box, and you measure the potential on this box over all possible translations. So you can get different configurations, different boxes, of course, right? And you count the total number of these configurations. So in general, total number of these configurations will be infinite if the potential, for example, takes infinitely many values.
And potentially you're talking about the U here. The
U.
interaction.
Yes.
Not the V.
U.
U, okay.
So we want the total number of configurations in the box of size n among the translation will be bounded by n to some power. So let me write down it more precisely. So what are we doing? We're translating U by vectors from Z2 and restricted to a box. Sorry, 0n squared. Restricted to a box. And count the number of different functions among this restriction. We want this number to be bounded by n to some power.
In particular, it takes a finite number of values.
Yes. In particular, it will take finitely many values, which is already a strong restriction, but that's not enough, because even if you have finitely many values, you can still have something like 2 to the n. These values are sufficiently randomly distributed. On the other hand, a lot of natural interaction potentials actually satisfy this property. For example, this potential, if f has finite support, has this property, because there is only like 2n possible different positions of the box. The rest will have just 0. Another example is, for example, periodic background, which is also be like this. And another non-trivial example is actually Fibonacci Hamiltonian, which I will not define. But OK, so this is one natural class of quasiperiodic operators that people consider, which gives singular spectrum. So, and turns out it also satisfies this property. And we're not gonna, it's not that interesting, but I'm just saying that there are some non-trivial things which satisfy this. So this property will be important for the proof in many places. So, and as I said, interaction potentials like this satisfy it automatically, and periodic backgrounds also satisfy, and some other stuff. OK, in particular, as Sasha mentioned, you can only take in finitely many values. So let's renumber these values. So let's let U1, U, n of U be the values of U. There are finitely many of them. So now I'm ready to formulate the main theorem, unless there are any questions about these definitions. They seem a little bit artificial, maybe, but you will see where they appear in the proofs. OK, so theorem 1. So which will be a localization theorem. So let epsilon greater than 0. There exists lambda 0 equals lambda 0 v epsilon. OK, so Cu. By Cu here, I mean these complexity parameters of U, not the actual U, such that the following is true. If lambda greater or equal than lambda 0, then so there exists another set omega, which will be the set of bad frequencies. So then there exists omega. Let's call it omega bad, subset of T1. So OK, so let me say what it depends on. Omega bad will depend on. OK, so lambda v u theta 1 theta 2 So omega bet will depend on everything, but omega bet will have Lebesgue measure less than epsilon, such that the operator H, so such that if omega is not in this set of bet frequencies, then H, theta 1, theta 2 has Anderson localization. And then there is this difference between symmetric and asymmetric cases. In the asymmetric case, it will have Anderson localization at all spectrum. No more questions to ask. For symmetric of V, for asymmetric V, on the whole spectrum. And for symmetric V, we'll have to remove several energies. And the energies that we have to remove, so the ones that we don't know about, will actually be the values of this interaction. So if we do not assume that condition that Sasha asked about, then they'll be translated by the average of V. So for symmetric V, so we have to assume that the energy is not very close to any of these values. So what does not very close mean? So for energies, E minus uj is thus equal to lambda divided by log lambda to some power mu, which will depend on complexity parameters of U. So we'll have to remove a pretty large intervals. So if lambda is large, the size of this interval grows almost as fast as lambda, but still a little bit slower than lambda. So relatively, with respect to the total size of the spectrum, we're still removing a small set. So we'll remove a subset of the spectrum of relatively small measure, and you can also show that it actually will have small density of states measure. So around each of these energies, you have to remove an interval which blows up as lambda goes to infinity, but it blows up a little bit slower than the total size of the spectrum. And since the number of intervals is bounded, then we still get something meaningful.
So in the asymmetric case, do you need to assume that your U has finitely many values or not?
Yes, I do. So asymmetric case also works only within this class. And this is very important. But you don't have to remove values from the energy. Yeah.
In the symmetric case, outside that range, it means that the eigenfunction does not decay exponentially. Like you cannot guarantee that.
Well, okay. So first, sorry, I got inequality in the wrong direction. Greater or equal.
For symmetric, for energies, what?
So E minus uj should be at least this.
Localization away from those.
Away from those energies. Yes. Sorry. So we don't know what happens in these regions. So we have one example, which will be theorem 2, which says that in some special case, you actually can have some AC spectrum there inside. But that example is a little bit more simple than the most interesting situation. So, but yes. So we have partial answer that this condition is important at least in some cases. So. Okay, so and then all the physics papers actually which show delocalization, they consider this cosine. So then I would speculate that the result that they get are dependent on the symmetries of the potential. So that if they took something else instead of the cosine, which is not symmetric, then they wouldn't have what they have. Okay, so this was theorem 1.
For instance, cosine squared would not be symmetric, right?
Cosine squared is symmetric because, oh, I see.
But Cosine squared.
I think it is okay. So I think it is symmetric because after you so it doesn't satisfy this average condition. After you shift, it becomes essentially cosine of the double argument, right?
Yeah.
And it has the same problem.
Because he's subtracting a constant to make it.
Yeah. Yeah, but if you take, for example, a combination of several cosines with even and odd frequencies, then you can make it asymmetric. So you can write down what it means for both this condition in terms of Fourier series. I mean, it will take some time to realize, but basically it has something to do with either all Fourier, I mean, sine and cosine ones, only even numbers or only odd numbers depending on sign. So and then you can easily construct examples of finitely many trigonometric functions that are asymmetric. So yes, so I know that for physics it's important that this should be a trigonometric polynomial because it means that the corresponding lattice interaction will be finite range. Yes. So but you can find them among trigonometric polynomials. That's okay. So this is the first theorem. Yeah.
So what is the statement about how this either coincides or doesn't coincide with the physics prediction is?
Okay. So
Catch that.
So part 2 says that localization statement doesn't contradict physics because it doesn't cover the whole spectrum.
So physics is saying there is some AC spectrum?
Yes. Well, physics say that there is some delocalization.
Okay.
So and our result says that, well, okay, so it's true that we cannot prove localization everywhere, so it doesn't contradict the fact there is delocalization.
Okay.
But first claim says that if physicists were considering asymmetric case instead, they would not get delocalization.
For large enough coupling.
For large enough coupling, yes, that's correct. So
so you don't make the asymmetric part quantitative, but I guess the lambda that you have to choose will depend upon how asymmetric it is.
It will, in a sense, yes, that's correct. And it will depend on many other things. So this lambda will be very different from the lambda which is required for single particle to be localized. It will be not like terribly larger, but it will be significantly larger. Okay, so this was theorem 1. So let me now talk about theorem 2. So let me write it here. So theorem 2 is about the following special case. Let V equals cosine, and the interaction will be the Hubbard type interaction. So it basically will support it on the diagonal. So u of n1 and 2 equals delta n1. Okay, some constant a, delta n1 and 2. So it will be supported on the diagonal. Particles interact only if they are in the same point. And this is actually the model which was considered in the physics papers. And now this model actually has some partial translational symmetry in the diagonal direction, because this potential now has diagonal translational symmetry. So it's natural to introduce two different phases. So let's say theta equals theta 1 plus theta 2 divided by 2. Eta equals theta 1 minus theta 2 divided by 2. So and then this is kind of a natural quasiperiodic parameter describing the system, and this can be considered as an extra coupling constant. So you would expect spectrum to be the same for different thetas, but different thetas give you different answers. So then the following is true. So first, if A, so the strength of interaction, is greater than some A0, which depends on lambda and eta, then, okay, so let me actually give first, before this, then let me give a general picture of what's going on with the spectrum of that model. So we are looking at the regime where, let's say, lambda is fixed and U has some extra large coupling in it. So, and U is this delta function. So U is basically a projection onto subspace of infinite but smaller dimension. So if A is much larger than lambda, then the spectrum of the model can be naturally split into two parts. So first there will be a component which is of the size lambda, let's say negative 10 lambda, 10 lambda. So it doesn't have to be the whole line segment that's contained here. There will be also a component shifted by A. So it's just because this term will be a projection operator with, well, multiple projection operator with eigenvalues 0 and A, and this will be perturbation of it. So 0 and A will be perturbed to neighborhood of 0 and neighborhood of A. And these results will be about this band. So I'll call this interaction band. So it's a part of the spectrum, but the interaction is really important. Okay, so then the following is true. So if interaction is very large,
these two bands overlap, right?
Well, if A is very large, they don't have to overlap. So I'm looking at the regime where A is much larger than lambda.
Okay, so they don't overlap.
They don't overlap. And it don't have to be like intervals. I'm just saying that the spectrum is contained in the union of intervals. So there is definitely something here. Yes. So because I'm assuming A is big. Yeah. So then the interaction band actually also has Anderson localization. So then interaction band has Anderson localization. So this is not for instance. It tells us that large interaction in general, if you fix eta, it cannot delocalize anything. But what you can do is you can do the following. You can fix some large A and then make the parameter eta very close to 1/2. So if A greater or equal than, let's say, A1 of lambda, and eta minus 1/2 is less or equal than some eta 0 depending on A, then interaction band has
How bad? So eta is always between -1, okay, -2 to
-1 and 1.
-1 and 1.
Well, it's everything's modulo 1, yeah.
Yeah, but for each eta it becomes worse and worse. You say that A should be bigger than something.
Sorry, for which eta?
Okay, so you ask A to be large enough. Okay,
Yes.
Assumption on lambda, but there is also, it depends on eta.
Yes.
And kind of dependence, it becomes bad near.
It's relatively explicit. So what I'm saying that it's a competition between, in the end it's going to be a competition between A and eta.
What is the reason why I don't have uniform bound that does not depend on eta?
Okay, so okay, so the case eta equals 1/2 actually means that the potential completely vanishes on the diagonal which supports the interaction. So, and this is bad. So, I mean, if I have time, I will explain the proof, but basically it follows from the proof. So, okay, so let me give a couple of comments. So, to study this interaction band, there is a way to reduce it to an effective nonlinear model on the support of the interaction. So, if it's separated from the bulk spectrum, this is important. So, net effective nonlinear model. Okay, so I'll write down how it's going to look like.
So you said it has non-trivial AC spectrum.
Yes.
But do you know that there's an interval where it's pure AC or not?
No, I don't know.
Okay.
I know that the C component is not trivial. Okay, so if you write down an effective one-dimensional model for this, so it's some computation which involves Lyapunov-Schmidt decomposition, which I probably don't have time to repeat, but the answer will be something like this. So it's going to be an operator on the diagonal. So which the diagonal can be identified with z. So it's essentially it's going to be operator on z. And the operator will look like this. It's going to be 1 over e Laplacian on the diagonal. So this Laplacian is different Laplacian because it's hopping not on the original lattice but on the diagonal. Plus essentially cosine eta, cosine, and omega plus theta. Plus some nonlinear terms, which are of 1 over e squared. This will be essentially the Hamiltonian on z, which will describe the model here. It will have a nonlinear term. And now what's going to happen? So if eta is fixed and e is large. So yeah, notice that e will be in this interval. So e will be of the order a. So a is large means e is large.
And the coupling constant not in here, or
well, yeah, coupling lambda will be here, but lambda is fixed, so we kind of ignore it. Yeah. So e approximately equal to a. So if e is large, it's the same as a is large, right? So if a is large, it means that the leading term of this operator will be quasi-periodic term, as long as cosine eta is not 0, right? So and small perturbation of a quasi-periodic term has localization. It's kind of hand-waving. It takes a lot of time to prove, but it can be done like this. So this is the intuition. On the other hand, if you fix e very large, so that this term, so you can ignore this term, and now take a small eta, then it's going to be a perturbation of the Laplacian.
You don't mean a small eta, but an eta for which cosine.
Yes, correct. Cosine, small cosine eta. Thanks. Then it's going to be a perturbation of the Laplacian. Laplacian kind of has AC spectrum, and then after perturbation, it will still have AC spectrum. This takes a lot of time to prove, but it can be done.
And the O of epsilon, the error term, that's a quasi-periodic function as well, or is that?
It's a nonlinear term. Actually, it will have some quasi-periodic structure, but the idea is that you can use. It's not local, nonlinear. Not very good. But there is a way to deal with it by kind of switching between the model on the diagonal and the whole model. So you
have to do a KAM kind of thing for that, or what? Describe that.
Not really. Okay, so you can do, as in localization proof, you start from estimates of green functions and do elimination of energy. So and this model is obtained by using Lyapunov-Schmidt decomposition or Schur decomposition. So and then you look at Schur decomposition on the level of Green's function. So then when you do Green's function, you're only interested in analyticity of the main term. For large deviations, you don't care about the second part. So you can deduce estimate for 2D Green's function from some 1D, essentially 1D Green's function, for which you know good large deviations. And once you have this Green's function, okay, so let me write a picture. This is diagonal. This is box in which you want to estimate Green's function. So by Lyapunov-Schmidt, it's restricted to large deviation. It's reduced to large deviation for some one-dimensional thing.
I don't know what you mean by large deviation here.
Well, essentially, the fact that the set of phases for which Green function is good is small. So that thing can be expressed as a ratio of determinants in one-dimensional case. So then it's about whether or not an analytic function comes very close for the same value to a long time. But yeah, so basically you can use Lyapunov-Schmidt to reduce question about Green's function to one-dimensional case. So, and then once you obtain the required data, you go back to the two-dimensional model and use this data from Green's function to finish the proof of localization using two-dimensional methods, which is not very hard. Yeah, so this was the idea of proof of theorem 2 with a lot of things I missed. So how am I doing on time? I wanted to make a few remarks about theorem 1, but I don't know.
Theorem 2, I mean, the whole reason that, I mean, the idea that's underlying this is that when the interaction is strong, your particles are essentially one on top of one another, and so the two particle nature is kind of
Yes, they're glued together into one quasi-particle, basically, and we study the dynamic of this quasi-particle, but only in part of the spectrum. We still don't, I still don't make any claims what happens here.
Sure. But the existence of AC spectrum is interesting. But do you think that there exists an example where you would still have AC spectrum with particles that are not glued together? So something with a much weaker interaction.
Yeah, that's a very good question. So let me actually, before talking about proof of theorem 1, if I even have time, let me make connection between theorem 1 and 2. So first, this example is symmetric, right? Cosine is symmetric. If it's asymmetric, nothing like this would be able to happen. So and then we are in the setting of part 2. Part 2 sets, we have two suspicious energy. In this case, because our interaction is this, there are two suspicious energies, 0 and A. And theorem 2 says that there is indeed something happens at the energy A which does not have to be localization. But what we do not know, and which seems very hard, is there a similar thing at 0 energy? Because if we're away from the bulk spectrum, we can kind of use Lyapunov-Schmidt to restrict everything to a one-dimensional subspace.
So you can't say what happens in that other...
No. Well, I think I can say that in some situations, well, in symmetric case, no. Just plain and simple, I don't know. So
in the asymmetric case, none of this happens.
Right. In asymmetric case, none of this happens. So this example shows that at least in one of the models, at least in one of the suspicious energies, there is indeed some delocalization.
But doesn't theorem 1 requires the infinity norm of U to be bounded by lambda?
Yes. So well, it's bounded by some constant times lambda, so you can originally choose that constant to be large enough so that it's smaller than the bound you get here. So I think there is a regime where both theorems are applicable. And then one of them says that there is localization outside suspicious energies, but there is delocalization near one of the suspicious energies. OK, so I don't know, how am I on time? Do I have to stop now, or?
5 minutes.
5 minutes, OK. So let me take a really quick glance into the proof of theorem 1. So I'll tell you the main thing where this condition of symmetry becomes important. So the proof is based on estimates of green functions. Green function is basically when we restrict operator on a box. And take the inverse. Okay, so let's say MM. And green function is also dependent on the parameters theta 1 and theta 2. So if we translate the parameters theta by n omega, let's say, it's the same as translating this box. So green function is a matrix element of the inverse operator. And
N and M belong to where?
Z2. So and the main idea of the proof of localization is the following, that we take something that's called generalized eigenfunction, which is a polynomially bounded solution of this equation. There is a theorem which says that the spectral measure is supported on the set of energies where there is this polynomially bounded solution. So then you can do the following thing. If you know that green function decays exponentially away from the diagonal, then so you can do the following. Using green function, so if you know that psi is bounded by polynomial somewhere on the boundary of the box, then inside of the box, if green function's elements decay exponentially, it will give exponential decay of the green function of the psi inside of the box. So and then by placing carefully boxes with good green functions at the appropriate positions, you can get exponential bottom psi. And so the first claim is the proof that if you fix a box, and yes, if you fix the box, then the set of thetas such that green function does not have exponential decay is small. So and the proof of this is done by the induction of scales. So you establish it for the initial scale. Okay, so okay, so so you first choose some size of the box. Then you consider the operator to be perturbation of its diagonal. Diagonal part has exponential decaying green function. And then you want, when you go to the next scale, you want to cover large box by small boxes. So, and basically you want to obtain exponential decay estimate of green function large box from estimate on the small boxes. And you know that small boxes are obtained by translation. So and then you allow a certain amount of bad boxes inside of big box. So basically you want, suppose this big box has size n bar, good box has size n. You want to show, so this is like the heart of the proof, that the number of bad boxes of size n in the box size n bar with some relation between n and bar is bounded by.
Bad boxes meaning you don't have great exponential decay.
Yeah. So number of bad n
in the smaller boxes.
Yeah. Is bounded by n bar to some power which is strictly less than 1. So then there is a way to glue these small good boxes into one bad box. Essentially, it's skipping.
You have to worry about the bad boxes being really bad.
Well, yes. So this is something that can be taken care of. But the important thing is that this bound. So because different positions of small boxes are obtained by translations, basically it reduces to counting points of the following type, and 1 omega and 2 omega. So counting points of a certain type, like trajectory of rational rotation, in some small set S of the parameters theta 1, theta 2. So set S subset of T2. So you want the number of these points to be bounded by some power less than 1. And then
What's S?
so S is a set of phases for which green function of the box of size n is bad. Sorry, I don't really have time to draw this. Okay, set of phases. So basically, it reduces to count a number of lattice points in some small set, which will have some algebraic structure. And then basically, you have to remove some frequencies for this bound to be true. So one way to do it is to remove some frequency vectors, which is what Burgin and Schlag is doing. And if we okay, so in our setting, we cannot remove vectors on the diagonal. And then there is a problem with this set S contains, for example, some thin diagonal segment. So the inductive statement would be that the set of parameters for which green function is bad has small section by line segment in any horizontal or vertical direction. That's Burgin and Schlag. And we want it to have small section by line segment any direction, because to deal with this kind of problems. And then this condition, we need to establish it on the initial scale to go further. And that initial scale reduces to the solution of the equation v of theta 1 plus v of theta 2 equals 0. So you want this to have no straight line segments. And then you can repeat this machinery and prove Green's function estimates. So there is a lot more work with elimination of energy, but unfortunately I'm kind of out of time.